Picture for a moment the endless expanse of the universe, a cosmos so vast that even light takes billions of years to cross it. Now, imagine an explosion so powerful it outshines entire galaxies, unleashing more energy in a few seconds than our Sun will produce in its entire lifetime. These are gamma-ray bursts, the most violent, mysterious, and fleeting events in the universe. And the most distant ones, they're like cosmic time capsules, carrying whispers from the infancy of everything we know. What makes these faraway eruptions so astonishing isn't just their mind-bending power. It's the fact that they're windows into the past, stretching back to a time when the universe was raw, chaotic, and barely recognizable. When scientists detect a gamma-ray burst from the edge of observable space, they're not just witnessing a cataclysmic event, they're peering into the ancient fires that shaped existence itself. Some of these bursts traveled for over 13 billion years before reaching us, their light surviving nearly the entire age of the cosmos just to deliver a single explosive message. But here's where it gets even wilder. The very existence of these distant gamma-ray bursts challenges what we thought we knew about the early universe. How could such impossibly bright explosions ignite so soon after the Big Bang? What kind of cosmic monsters, collapsing stars, black holes, or something even stranger, could unleash such fury? And what secrets do these bursts hold about the formation of the first galaxies, the birth of heavy elements, or even the fabric of space-time? That's what makes this journey so thrilling. Over the next 30 facts, we'll dive into the most distant gamma-ray bursts ever discovered, unraveling their mysteries, decoding their origins, and uncovering the mind-blowing truths they reveal about our universe's most distant, violent, and awe-inspiring corners. Buckle up, because we're about to travel to the edge of everything. Gamma-ray bursts are the universe's ultimate fireworks brief, violent flashes of energy so intense they momentarily outshine everything else in the cosmos. But what exactly are they? Picture a supernova on steroids. These bursts are concentrated beams of gamma rays, the highest energy form of light, erupting from distant galaxies when massive stars collapse or when ultra-dense objects like neutron stars collide. Lasting anywhere from milliseconds to several minutes, they come in two main flavors, short and long bursts. Short gamma-ray bursts, lasting under 2 seconds, are usually the aftermath of two neutron stars spiraling into each other, unleashing gravitational waves alongside their explosive farewell. Long bursts, stretching beyond 2 seconds, signal the death throes of colossal stars, ones dozens of times heavier than our Sun, imploding into black holes with such force that their dying screams rip across the universe. What makes them truly staggering isn't just their raw power, though a single burst can release more energy in seconds than our Sun will emit in 10 billion years. It's the sheer unpredictability. Unlike supernova, which may brighten over days, gamma-ray bursts vanish almost as quickly as they appear, leaving astronomers racing against time to catch them. Imagine trying to study a lightning bolt in a pitch-black storm. Only this lightning comes from billions of light years away. Detecting these bursts is like cosmic archaeology. Their light, traveling across eons, carries clues about the universe's most extreme environments. Some originate from regions where stars formed just a few 100 million years after the Big Bang, offering snapshots of the cosmos in its infancy. Others hint at exotic physics, magnetic fields trillions of times stronger than Earth's, or jets of particles moving at nearly the speed of light. Yet for all their brilliance, gamma-ray bursts remain elusive, flickering into existence and fading before we can fully grasp their secrets. That's why every detection, especially of the most distant ones, is like unearthing a message in a bottle, shoved into the cosmic currents billions of years ago, finally washing ashore in our telescopes. The story of gamma-ray bursts begins not with astronomers peering through telescopes, but with Cold War satellites designed to spy on nuclear tests. In the 1960s, the United States launched the Vela satellite silent sentinels orbiting Earth to detect gamma rays from secret atomic explosions. But these watchful eyes kept catching something unexpected: brief, intense flashes of gamma radiation coming not from Earth but from deep space. At first, scientists thought they might be glitches. The signals were so strange that researchers spent years verifying the data before even publishing their findings. When they finally did in 1973, it kicked off one of the greatest cosmic detective stories in history. For decades, no one knew what caused these mysterious bursts. Were they coming from within our own galaxy or from billions of light years away? The debate raged until the 1990s, when two breakthroughs changed everything. First, the Compton Gamma Ray Observatory mapped hundreds of bursts, and they were scattered evenly across the sky, a telltale sign they originated far beyond the Milky Way. Then, in 1997, the Italian-Dutch satellite Bepo-SX pulled off a miracle. It pinpointed the exact location of a gamma ray burst fast enough for ground telescopes to capture its fading afterglow. For the first time, astronomers saw the host galaxy, a faint speck so distant it confirmed these explosions were happening at the edge of the observable universe. That discovery rewrote astrophysics. Suddenly, these fleeting flashes weren't just cosmic oddities, they were the death cries of massive stars in galaxies so far away their light had traveled for most of the universe's existence. Later missions like Swift and Fermi built on this legacy, automating the hunt for bursts and linking them to supernova and neutron star collisions. Each new detection peeled back another layer of the mystery, revealing how these titanic events seed the cosmos with heavy elements, test the limits of Einstein's physics, and even help measure the expansion of space itself. What started as an accidental find on military satellites has become one of astronomy's most thrilling frontiers, proving once again that the universe loves to surprise us. Here's something that will bend your mind when we detect a gamma ray burst from the edge of the observable universe. We're not just seeing an explosion. We're looking into the past. Light doesn't travel instantly. It moves at the fastest speed possible in our cosmos, but across billions of light years, even it takes time. So when a burst from 13 billion light years away finally reaches Earth, what we're witnessing isn't happening now. It's an echo of an event that occurred when the universe was less than a tenth of its current age, a time so ancient that galaxies were still assembling themselves from primordial gas. This time delay turns gamma ray bursts into cosmic time capsules. Their light carries fingerprints from an era when the first stars were igniting, before planets like Earth even existed. By studying the wavelengths absorbed or emitted during these bursts, astronomers can reconstruct the chemical makeup of the early universe. They've found traces of elements like carbon and oxygen, ingredients essential for life, already present in the cosmos just a few 100 million years after the Big Bang. That discovery alone rewrote textbooks, proving that the universe evolved faster and more violently than anyone predicted. But the implications go even deeper. Because these bursts are so bright, they act like interstellar flashlights, illuminating the gas clouds and galaxies that lie between them and us. It's a phenomenon called the Lyman alpha forest, where the burst's light passes through countless layers of hydrogen, each absorbing specific wavelength. By decoding these absorption lines, scientists create a map of cosmic structure over eons, revealing how the universe's scaffolding changed as galaxies formed and merged. And here's where it gets really wild. Some of the most distant bursts ever recorded come from a time when the universe was still opaque, a murky soup of ionized gas. Their existence tells us that the first stars and black holes must have formed astonishingly quickly, pumping out enough ultraviolet radiation to rip electrons from atoms in a process called reionization. Without these early bursts, we might never have known how fast the universe transformed from a dark, featureless void into the star-filled expanse we see today. So every time a gamma ray burst flickers on in the depths of space, it's not just a flash of light. It's a message from the dawn of time itself. If you want to talk about cosmic distance records, gamma ray burst GRB 090423 is in a league of its own. Detected in April 2009 by NASA's Swift satellite, this spectacular explosion holds the title as the most distant gamma ray burst ever observed, a staggering 13 billion light-years away from Earth. To put that incomprehensible distance into perspective, the light from this burst began its journey when the universe was just 630 million years old, a mere infant by cosmic standards. That means we're witnessing the death throes of one of the very first generation of stars, erupting in an era when galaxies were barely beginning to assemble. What makes GRB 090423 so revolutionary isn't just its record-breaking distance. Its existence forced astronomers to rethink how quickly the cosmos could produce such incredibly luminous events after the Big Bang. This wasn't just any star, it must have been a true behemoth, dozens of times more massive than our Sun, collapsing in a catastrophic supernova or hypernova to unleash a gamma-ray jet powerful enough to remain detectable across 13 billion years of expanding space. The fact that we can still see its afterglow today means the early universe was far more dynamic and violent than we ever imagined, capable of forging and destroying titanic stars at breakneck speed. But the real treasure lies in what this burst revealed about the universe's murky beginnings. When GRB 090423 detonated, space was still emerging from the cosmic dark ages, a period before the first stars flooded the universe with light. Yet its spectrum showed traces of heavy elements, proving that even at this early stage, stars had already lived, died, and seeded space with the raw materials for planets and life. Without bursts like this, we might never have known how quickly the first stars transformed the cosmos from a featureless void into the chemically rich universe we inhabit today. So while GRB 090423 lasted mere seconds in our telescopes, its legacy has illuminated the darkest chapter of cosmic history. Measuring the distance to gamma-ray bursts requires one of astronomy's most powerful tools, redshift, represented by the letter Z. Here's how it works. As the universe expands, light traveling through space stretches along with it, shifting toward longer, redder wavelengths, a phenomenon called cosmological redshift. The farther away an object is, the more its light has stretched and the higher its redshift value. For nearby galaxies, Z might be a tiny decimal, but for gamma-ray bursts at the edge of the observable universe, redshift skyrockets into the double digits, telling us we're glimpsing events from an era when the cosmos was a fraction of its current size. High redshift gamma-ray bursts are extraordinarily rare, and for good reason. Detecting them means catching a fleeting explosion from an epoch when galaxies were sparse and stars few. Add to that the challenge of measuring redshift itself. Unlike galaxies, which shine steadily enough for detailed spectral analysis, gamma-ray bursts vanish in minutes, leaving only a fading afterglow. Astronomers have mere hours to swing ground-based telescopes toward the burst's location, capture its light, and dissect its spectrum for telltale absorption lines, the fingerprints of distant elements that reveal redshift. The technical hurdles don't end there. The most distant bursts often originate in environments choked with primordial gas, their light further dimmed by cosmic expansion. By the time their photons reach Earth, they've been stretched into the infrared, a wavelength range where Earth's atmosphere absorbs much of the signal. That's why missions like the James Webb Space Telescope are game-changers, peering into the infrared with unprecedented clarity to decode redshifts for bursts that would otherwise slip through our fingers. Each successful measurement is a minor miracle, a brief window into the universe's most elusive and ancient explosions. But when we do catch a high Z gamma ray burst, the payoff is immense. These extreme redshifts act as cosmic mile markers, helping astronomers reconstruct the universe's expansion history and test theories about dark energy. They also reveal how quickly the first stars and galaxies formed, proving that the early universe was far more dynamic than we ever imagined. So every time astronomers pin down a redshift for one of these distant bursts, they're not just measuring distance, they're rewriting the timeline of cosmic evolution. Long before galaxies spiraled into their familiar shapes, before planets formed and life emerged, the universe passed through a twilight era known as the cosmic dawn, a time when the first stars flickered to life in an endless sea of darkness. Gamma-ray bursts from this primordial epoch are like messages in a bottle, cast across billions of years to tell us how the cosmos shook off its shadowy beginnings. These ultra-distant explosions aren't just spectacular light shows, they're forensic evidence of the universe's most transformative phase, reionization. Picture a universe still cloaked in fog. After the Big Bang, space was filled with a thick, neutral hydrogen gas that absorbed starlight, keeping everything dark. Then, around 200 million years later, the first massive stars ignited, their ultraviolet radiation shredding hydrogen atoms into charged particles. This process, called reionization, burned away the cosmic fog, turning the universe transparent and allowing light to travel freely for the first time. But how do we know this happened so quickly? Enter gamma-ray bursts from the cosmic dawn. Their light carries the chemical fingerprints of the gas they passed through, revealing patches of ionized and neutral hydrogen along the way, like a lighthouse beam cutting through mist. One of the most revealing bursts, GRB 050904, erupted when the universe was just 900 million years old. Its afterglow spectrum showed something astonishing, gaps where light had been absorbed by both ionized gas and lingering pockets of neutral hydrogen. That proved reionization wasn't instantaneous. It was a messy, uneven process, with some regions clearing faster than others. Without these bursts, we'd have no way to map this critical transition. They're the only light sources bright enough to pierce the veil of the early universe and show us how the cosmos turned on the lights, but the surprises don't end there. The sheer existence of cosmic dawn gamma-ray bursts suggests the first stars were unlike anything in today's universe. To produce such violent explosions so soon after the Big Bang, these stars must have been colossal, hundreds of times the mass of our Sun, burning hot and fast before collapsing in cataclysmic hypernova. Their deaths didn't just illuminate the early cosmos, they forged heavy elements like carbon and iron, scattering the building blocks of future planets and life across the void. Every gamma-ray burst from this era is a snapshot of creation in action, a fleeting glimpse of the fires that shaped everything we know. The most violent deaths in the universe don't come quietly. They announce themselves with gamma-ray bursts so powerful they can outshine galaxies. And when it comes to long gamma-ray bursts, we're witnessing the final, explosive moments of stars that make our Sun look like a flickering candle. These aren't just any stars, they're colossal, fast-spinning behemoths, dozens of times more massive than our Sun, living fast and dying young in a spectacular collapse known as a collapsar. At the end of their short, furious lives, these stars don't just fade away. Their cores implode under their own gravity, compressing into a black hole in seconds. But here's where things get explosive. As the star's outer layers come crashing down, they don't just vanish into the black hole's maw. Some of that material gets whipped into ultra-fast jets along the star's rotation axis, punching through the collapsing star at nearly the speed of light. These jets, blazing with intense gamma radiation, are what we see as a long gamma-ray burst, a final, brilliant flash before the star vanishes forever. This process is so extreme it earns another name, hypernova. Imagine a supernova but cranked up to unimaginable levels. Where a typical supernova might outshine its galaxy for weeks, a hypernova releases hundreds of times more energy, briefly becoming the brightest thing in the observable universe. The difference comes down to physics. Normal supernova occur when a star's core collapses into a neutron star, but hypernova go further, collapsing straight into a black hole while funneling energy into those narrow, ultra-relativistic jets. It's the difference between a firework and a directed energy blast. The aftermath is just as dramatic. Hypernova don't just leave behind black holes. They're cosmic forges, creating and hurling heavy elements like gold, platinum, and uranium across space. Without these catastrophic explosions, the universe would lack the raw materials for planets, and life as we know it wouldn't exist. Every long gamma-ray burst is a reminder that even in death, the universe's most massive stars shape the cosmos in ways we're only beginning to understand. While long gamma-ray bursts steal the spotlight with their brilliant, minutes-long flashes, their shorter cousins pack a different kind of cosmic punch. Short gamma-ray bursts lasting under 2 seconds come from a completely different breed of catastrophe. Instead of a dying star's last gasp, these intense bursts are the universe's way of announcing a violent merger between two of the most extreme objects in existence, neutron stars. Picture this: 2 city-sized stellar corpses, each more massive than our Sun but crushed into a sphere barely 12 miles wide, locked in a deadly spiral. As they collide, they unleash gravitational waves, fling out glowing debris rich in gold and platinum, and, for a fleeting instant, fire off jets of gamma rays so focused they can be seen across the cosmos. Here's what makes these mergers so explosive. Neutron stars are so dense that a single teaspoon of their material would weigh 1 billion tons on Earth. When 2 of them finally crash after circling each other for eons, the impact creates a black hole almost instantly, while the leftover material forms a swirling, super-hot disk that can launch particle jets at near light speed. These jets are what we detect as short gamma-ray bursts, cosmic lightning bolts signaling the birth of something new from the wreckage of the old. Yet when we look to the very edges of the universe, something curious happens. Almost every gamma-ray burst we've detected from the cosmic dawn is a long burst, not a short one. The reason comes down to time. Neutron star mergers are slow to develop. It can take billions of years for 2 neutron stars to inch close enough to collide. But in the universe's early days, galaxies were smaller, stars were younger, and there simply hadn't been enough time for enough neutron star binaries to form and merge. Long bursts, on the other hand, come from massive stars that live fast and die young, exploding within just a few million years of their birth. In a young universe still filling with its first generations of stars, these hypergiants were the only things capable of producing gamma-ray bursts at all. That's why the most distant gamma-ray bursts act like cosmic archaeologists. They're not just telling us about the deaths of stars, but about the conditions of the universe when those stars were born. Every long burst from the edge of space is a timestamp, marking an era when the cosmos was too young for the quiet, patient collisions of neutron stars. Instead, it was a time of titanic explosions, blazing brief and bright across the dark, primordial sky. When a gamma-ray burst erupts across the cosmos, its initial flash of high-energy light is just the beginning of the story. What follows is something even more valuable to astronomers: the afterglow. This lingering radiation, detectable across the electromagnetic spectrum from X-rays to radio waves, acts like a cosmic fingerprint, revealing secrets about the burst's environment, distance, and even the galaxy that birthed it. Imagine turning on a flashlight in a pitch-black room. The initial burst is the moment you flip the switch, but the afterglow is the light reflecting off the walls, exposing details you'd never see otherwise. The afterglow begins minutes after the initial explosion, as the jet of material collides with surrounding gas and dust at nearly light speed. This collision creates a shock wave that heats the material to extreme temperatures, causing it to glow across multiple wavelengths. X-rays, the first to be detected, often reveal the burst's precise location, while ultraviolet and visible light expose the chemistry of the host galaxy. Infrared observations peer through dust clouds to uncover hidden star-forming regions, and radio waves trace the motion of ejected material over weeks or months. Together, this multi-wavelength treasure trove lets astronomers piece together the full narrative of the burst's aftermath. But the real magic happens when scientists combine these observations. Take GRB 030329, for example. Its X-ray afterglow led researchers to a faint galaxy 13 billion light-years away, while its optical spectrum revealed something astonishing: iron and magnesium in a galaxy so young these elements shouldn't have existed in abundance yet. That told us the first stars must have formed and died explosively, seeding the cosmos with heavy metals far earlier than predicted. The afterglow's longevity is another clue. Some fade within hours, suggesting the burst occurred in a sparse region of space. Others, like GRB 130427a, lingered for months, hinting at a dense environment rich with material to fuel the glow. These variations act like cosmic weather reports, describing the conditions in galaxies so distant they'd otherwise be invisible to us. And let's not forget the radio afterglow, often the last to appear and the slowest to fade. By tracking how this emission changes over time, astronomers can map the expansion of the burst shockwave, measuring the energy of the original explosion with precision. It's like watching the ripples from a stone thrown into a pond, except the pond is the universe, and the ripples carry the echoes of a stellar cataclysm. Without afterglows, gamma-ray bursts would remain fleeting mysteries, their origins lost in the dark. But thanks to this multi-wavelength glow, every burst becomes a roadmap, one that guides us not just to the event itself, but to the distant corners of the cosmos where galaxies are born, stars die, and the universe writes its most dramatic stories in light. Before 2004, catching gamma-ray bursts in the act was like trying to photograph lightning with a Polaroid. By the time astronomers swung their telescopes toward the burst's coordinates, the show was usually over. Then NASA's Swift satellite changed the game. Named for its speed, this observatory wasn't just designed to detect bursts, it was built to hunt them down in real time. Imagine a celestial watchdog orbiting Earth with X-ray eyes wide open, waiting for the sky to flash. The moment Swift's Burst Alert telescope senses a gamma-ray burst, it doesn't wait for orders from the ground. Within seconds, it pivots autonomously, pointing its X-ray and ultraviolet telescopes at the explosion while simultaneously alerting observatories worldwide. This rapid response system turned Swift into the ultimate cosmic first responder, transforming gamma-ray bursts from fleeting mysteries into tangible targets for study. But Swift didn't work alone. Launched in 2008, NASA's Fermi Gamma-Ray Space Telescope brought an entirely new perspective to the hunt. While Swift specializes in rapid localization, Fermi's Large Area Telescope detects gamma rays across a staggering range of energies from thousands to billions of electron volts. That's like upgrading from a magnifying glass to an electron microscope. Fermi's wide field of view and ultra-sensitive detectors made it perfect for spotting the highest energy gamma-ray bursts, including some so distant their light had been stretched nearly into oblivion by cosmic expansion. Together, these two telescopes formed an unbeatable team. Swift pinpoints the burst's location within minutes, while Fermi dissects its energy spectrum, revealing details about the explosion's physics that would otherwise be lost. The impact of this tag-team approach can't be overstated. Before Swift and Fermi, astronomers had recorded only a handful of gamma-ray bursts with confirmed redshifts critical for measuring their distances. Today, thanks to Swift's agility and Fermi's precision, that number has skyrocketed into the hundreds, including some of the most distant bursts ever seen. Take GRB 080916C, a burst Swift detected in 2008. Within 75 seconds of the initial flash, Swift had not only located the burst but also captured its fading X-ray afterglow, allowing ground telescopes to measure a redshift of 4.35. placing it over 12 billion light-years away. Fermi, meanwhile, revealed that this burst's gamma rays carried energies surpassing 30 billion electron volts, proving that even the universe's earliest explosions could accelerate particles to near light speed. What makes these telescopes truly revolutionary isn't just their technical specs, it's how they democratized gamma-ray burst science. By automatically broadcasting burst coordinates to astronomers worldwide within minutes, Swift and Fermi turned every ground-based telescope into a potential collaborator. Suddenly, a lone grad student in Chile or a hobbyist with a backyard telescope could contribute to cutting-edge research, chasing afterglows or measuring host galaxies. This global network of eyes on the sky turned gamma-ray bursts from obscure curiosities into one of astronomy's most collaborative frontiers. Perhaps their greatest legacy, though, lies in the surprises they've uncovered. Fermi's detection of GRB 130427 in 2013 shattered expectations anew by burst so energetic it briefly outshone the entire Milky Way in gamma rays, challenging theories about how particles behave in these extreme environments. Swift's observations of GRB 060218 in 2006 revealed a supernova connection no one had predicted, linking long bursts to a rare class of ultra-energetic stellar deaths. Every burst these telescopes catch adds another piece to the puzzle, proving that even after decades of study, the universe still has plenty of gamma-ray secrets left to share. One of the most fascinating tools in gamma-ray burst astronomy isn't a telescope or a satellite. It's a simple graph that reveals an astonishing cosmic pattern. Known as the Amati relation, this powerful correlation connects two key properties of gamma-ray bursts: their total energy output and the frequency at which they shine brightest. Picture throwing rocks into a pond. The bigger the splash, the higher the waves. The Amati relation shows something similar on a cosmic scale. The more energetic a gamma-ray burst is overall, the higher its peak frequency tends to be. This seemingly simple connection has revolutionized how astronomers study these explosions, especially those so distant their light is barely detectable. Why does this matter? Because the Amati relation gives scientists a way to estimate a burst's distance without relying solely on redshift measurements, a crucial workaround when dealing with ultra-distant explosions. Normally, calculating cosmic distances requires catching a burst's afterglow quickly enough to measure redshift, which can be hit or miss for the most fleeting events. But by analyzing the burst's gamma-ray spectrum, how its energy is distributed across different frequencies, researchers can plug the numbers into the Amati relation and get an immediate estimate of how far away the explosion occurred. It's like having a cosmic ruler built into the burst itself. The physics behind this relationship is just as compelling as its utility. The correlation suggests that despite their mind-boggling power, gamma-ray bursts aren't random. There's an underlying order to how these relativistic jets release energy, likely tied to the properties of their central engines, whether a newborn black hole or a rapidly spinning neutron star. The most energetic bursts, often linked to hypernova, tend to produce higher frequency gamma rays because their jets are more concentrated and powerful. Less energetic bursts, like those from neutron star mergers, peak at lower frequencies. This consistency across billions of light-years implies universal physics at work. No matter where or when a burst happens, the same fundamental rules apply. But the Amati relation isn't just a theoretical curiosity. It's been put to the test with remarkable results. When applied to GRB 080319b, a burst over 12 billion light-years away, the relation predicted an energy output consistent with independent redshift measurements, confirming its reliability. It's also helped resolve puzzles like the case of GRB 980425, whose unusually low energy initially made astronomers question whether it was a gamma-ray burst at all. The Amati relation placed it firmly in the gamma-ray burst family, just an unusually faint member, a cosmic outlier that helped define the rule's boundaries. What makes this discovery even more valuable is how it extends our reach into the early universe. For bursts so distant their afterglows fade before telescopes can catch them, the Amati relation offers a lifeline, a way to gauge their importance even when traditional methods fail. As we push observations further toward the cosmic dawn, this subtle correlation between energy and frequency may become one of our most trusted guides, revealing the lives and deaths of the universe's first stars through the echoes of their explosive final moments. Gamma-ray burst 080916C wasn't just another flash in the cosmic dark, it was a detonation so violent it redefined what we thought possible. Detected by the Fermi Gamma-ray Space Telescope on September 16, 2008, this burst unleashed more energy in a few seconds than the Sun will emit in its entire 10 billion-year lifetime. Its gamma rays, traveling over 12 billion light-years from a time when the universe was just 1.8 billion years old, carried energies exceeding 30 billion electron volts, so high that astronomers initially questioned whether their instruments had malfunctioned. But this was no glitch. GRB 080916C was a real event, and its existence forced scientists to rewrite the rules of high-energy astrophysics. What made this burst so extraordinary wasn't just its raw power, but the clues it carried about the physics of relativistic jets. Most gamma-ray bursts follow predictable patterns. Their light curves rise, peak, and fade in known ways. But 080916C defied expectations. Its emission arrived in multiple distinct waves, each more energetic than the last, like a cosmic orchestra building to a crescendo. The first pulse, relatively faint, was followed by a second wave 5 times stronger, and then a final, cataclysmic surge that outshone them both. This staggered release suggested something unprecedented, a central engine, likely a newborn black hole, that kept reactivating, pumping fresh energy into the jet long after the initial collapse. The implications ripple across decades of research. For one, the burst's extreme energies challenge models of how particles accelerate in these jets. Traditional theories suggested gamma rays beyond 10 billion electron volts shouldn't survive such a long journey. They'd interact with the cosmic microwave background and dissipate. Yet here they were, arriving intact. This forced physicists to consider alternative explanations. Perhaps the jets were even more focused than assumed, or maybe magnetic fields within them were boosting particle energies to previously unimaginable levels. Then there's the burst's cosmic context. GRB 080916C erupted during the epoch of peak star formation, a time when galaxies were churning out new suns at a ferocious rate. Its host galaxy, though too faint to see directly, must have been a stellar factory, breeding the kind of massive, unstable stars capable of such an explosion. The burst's heavy element signature, detected in its afterglow, confirmed this. It was enriched with metals forged in earlier supernova, proof that its birthplace had already cycled through generations of stars. For astronomers, this was like finding a fossil from the universe's most prolific era of stellar birth and death. Perhaps the most startling revelation, though, was how this single event bridged 2 eras of astronomy. The burst's lower energy gamma rays were spotted by Fermi, while its highest energy photons were later identified in data from the now defunct CGRO satellite. By combining these observations, scientists realized they were seeing the same phenomenon across an unprecedented energy range, from thousands to billions of electron volts. That synergy confirmed a long-held suspicion: gamma-ray bursts aren't just bright flashes, they're cosmic particle accelerators capable of energizing matter to velocities approaching light speed. Even today, 080916C remains a benchmark. New telescopes like the Cherenkov Telescope Array now scan the skies for similar ultra-high-energy bursts, hoping to catch one closer to home. Meanwhile, theorists still wrestle with its layered light curve. testing whether supermassive stars with complex core structures could explain its stop-start energy release. Every new discovery in gamma-ray burst science is measured against this titanic explosion, a reminder that the universe's most violent events often leave the most enduring lessons. Gamma-ray bursts don't just vanish after their initial explosion, they leave behind a trail of illuminated cosmic breadcrumbs. As their radiation races across the universe, it acts like the ultimate flashlight, piercing through clouds of gas, dust, and even entire galaxies that would otherwise remain invisible to us. This phenomenon turns GRBs into cosmic lighthouses, casting their beams through the vast darkness and revealing the hidden structure of the universe. Every atom, every molecule that lies along their path leaves a unique fingerprint on the burst's light, allowing astronomers to map the chemical makeup of space across billions of years. Take the case of GRB 121024a, a burst detected in 2012. When its light reached Earth, researchers discovered something extraordinary: dozens of dark absorption lines in its spectrum, each corresponding to elements like magnesium, silicon, and iron in distant gas clouds. These weren't just random blobs of matter. They were snapshots of the cosmic web, the intricate scaffolding of filaments and voids that connects galaxies across the universe. By analyzing how these lines shifted and spread, scientists could reconstruct the density, temperature, and even motion of gas along the burst line of sight, some of it untouched since the universe's earliest days. But the real magic happens when gamma-ray bursts cross paths with galaxies. Imagine a GRB's light slicing through a galaxy's outskirts where diffuse gas drifts between stars. As the radiation passes through, certain wavelengths get absorbed, creating a chemical shadow in the burst spectrum. These shadows tell us what the galaxy is made of, not just its stars, but the raw material floating between them. GRB 060428, for example, revealed a distant galaxy rich in carbon and oxygen, elements forged in previous generations of stars and then blown into space by supernova. Without the burst's backlighting, that galaxy would have been too faint to study in such detail. Even more astonishing is how these cosmic lighthouses reveal the universe's evolving chemistry. Some of the most distant bursts, like GRB 080916c, show absorption lines from elements that shouldn't have existed so soon after the Big Bang. Their presence proves that stars were already churning out heavy elements within the first few 100 million years of cosmic history, far earlier than models predicted. It's as if the universe got a head start on building the ingredients for planets and life. Then there's the intergalactic medium, the sparse gas filling the voids between galaxies. Normally, this material is nearly impossible to observe directly. But when a gamma-ray burst's light travels for billions of years, even the faintest wisps of hydrogen leave traces in its spectrum. These signals form what astronomers call the Lyman alpha forest, a series of absorption lines that act like mile markers for cosmic expansion. Each line corresponds to a different density of gas at a different distance, creating a 3D map of the universe's large-scale structure. GRBs observed by the Very Large Telescope, like GRB 140519a, have used this technique to probe regions of space so diffuse they contain only a few atoms per cubic meter. What makes gamma-ray bursts uniquely powerful for this work is their brightness. Unlike quasars, another common backlight for cosmic studies, GRBs can outshine their host galaxies by a factor of millions, making them visible across the entire observable universe. Their intense light also penetrates dust that would obscure other sources, allowing researchers to study regions normally hidden from view. And because they're transient events, their light doesn't drown out the fainter absorption features the way a steady quasar might. It's like using a camera flash to capture details in a dark room, brief but illuminating. The implications stretch beyond just mapping gas. Some bursts have revealed galaxies that traditional surveys missed entirely, lurking in the shadows of the cosmic web. Others, like GRB 070125, showed evidence of large-scale magnetic fields threading through intergalactic space, a discovery that could explain how cosmic rays accelerate across such vast distances. Every time a gamma ray burst flickers to life, it doesn't just tell us about the explosion itself. It turns the entire universe into a giant chemistry lab with the burst's light as our spectrometer. So the next time you hear about a gamma ray burst, remember it's not just a flash in the dark. It's a beacon shining through the cosmos and exposing secrets hidden for billions of years. From the ghostly trails of ancient hydrogen to the metal-rich winds of newborn galaxies, these explosions don't just light up the sky, they illuminate the very fabric of the universe. One of the biggest hurdles in studying gamma ray bursts from the universe's edge isn't just their distance, it's the cosmic dust that cloaks them like a veil. In the ancient galaxies where many of these bursts originate, thick clouds of silicate and graphite particles drift between stars, absorbing and scattering visible light. This interstellar dust doesn't just dim the afterglow, it can completely obscure it from optical telescopes, leaving astronomers with only a fraction of the story. Picture trying to watch a fireworks display through dense fog. The brightest flashes might still be visible, but the intricate details and lingering smoke trails vanish into the haze. That's the challenge dust poses for GRB hunters, but where dust creates obstacles, infrared astronomy opens doors. Because infrared light has longer wavelengths than visible light, it slips past dust grains with ease, like radio waves passing through walls. When a gamma ray burst's afterglow gets blocked in optical wavelengths, its infrared emission often shines through, carrying critical information about the burst's energy, host galaxy, and even the dust itself. NASA's Spitzer Space Telescope proved this in 2007 with GRB 070318, a burst whose visible afterglow was completely masked by dust. Spitzer's infrared eyes revealed not just the afterglow, but also the composition of the obscuring material tracing grains forged in the atmospheres of ancient stars. Modern missions like the James Webb Space Telescope have turned this work into high-resolution science. JWST's unparalleled infrared sensitivity allows it to dissect dust-obscured bursts in galaxies over 13 billion light-years away, analyzing their chemistry and temperature with precision. For GRB 221009A, detected in 2022, JWST didn't just peer through the dust, it identified complex organic molecules within it, suggesting that even in the universe's first galaxies, the building blocks for life were already present. The fight against cosmic dust doesn't end with infrared. Some observatories, like the Atacama Large Millimeter Array, target even longer wavelengths, millimeter and submillimeter radiation, that penetrate the thickest dust clouds. Others, like the Hubble Space Telescope, combine ultraviolet and optical data to model dust scattering effects, effectively reverse engineering its properties from how it distorts the afterglow's light. Each wavelength reveals another layer of the puzzle, proving that while dust might hide gamma-ray bursts from plain sight, it can't keep their secrets forever. What makes these dusty bursts especially valuable is what they tell us about their host environments. Galaxies choked with dust are often stellar nurseries, where rapid star formation generates both massive stars, the kind that produce long gamma-ray bursts, and the dust that shrouds them. By studying how much light these bursts lose to dust absorption, astronomers can map star-forming regions across cosmic time, tracking how the universe's dust production evolved from its gritty beginnings to the present day. Every dust-dimmed afterglow is a clue not just about the burst itself, but about the dusty cradles where galaxies are born. One of Einstein's most startling predictions was that massive objects could bend light itself, a phenomenon called gravitational lensing. Today, this cosmic trick of the light isn't just a curiosity, it's a powerful tool for spotting gamma-ray bursts so distant they'd otherwise be invisible. Imagine a magnifying glass floating in space, but instead of glass, it's an entire galaxy or cluster of galaxies warping the fabric of space-time around it. When a gamma-ray burst happens to lie perfectly behind one of these cosmic lenses, its light gets stretched, amplified, and sometimes even duplicated, like a flickering candle reflected in a funhouse mirror. Suddenly, a burst that should have been too faint to detect blazes into view, giving astronomers an unexpected front-row seat to an explosion from the edge of time. This lensing effect doesn't just make faint bursts brighter, it twists their light in ways that reveal hidden details. Take GRB 200323A, a burst magnified by a foreground galaxy cluster. The lensing didn't just amplify its glow, it split the burst's afterglow into 4 distinct images, each arriving at Earth at slightly different times. By comparing these delayed echoes, scientists could map the distribution of dark matter in the lensing cluster, an invisible halo shaping the light like hands molding clay. The burst's stretched-out spectrum also exposed gas clouds in the lensing galaxy itself, showing how its chemical makeup differed from the pristine environments of the early universe. But gravitational lensing does more than magnify, it also distorts. When GRB 050309's light passed through a massive elliptical galaxy, the lens stretched its afterglow into a faint arc, smearing its features like ink on wet paper. That distortion turned out to be a blessing in disguise. By analyzing how the galaxy's gravity warped the burst's light, researchers calculated the precise mass of the lensing galaxy, including its unseen dark matter component. It was like using a gamma-ray burst as a cosmic scale, weighing structures billions of light-years away with nothing but their gravitational fingerprints. The most tantalizing lensed bursts, though, are those that act as time machines. Because lensed light takes multiple paths around a galaxy or cluster, some routes are longer than others. That means a single burst can reappear in telescopes days, weeks, or even years after its initial flash, a delayed replay of the same cataclysmic event. In 2014, astronomers spotted just such a repeating afterglow from GRB 130603A. Its light bent around a massive galaxy so that the later images arrived nearly 3 weeks after the first. This time delay isn't just a curiosity, it lets scientists compare the burst's early and late stages in unprecedented detail, like watching an explosion in slow motion from multiple angles. Yet for all its advantages, gravitational lensing is a double-edged sword. The same magnification that makes distant bursts detectable also scrambles their true properties. A lensed burst might appear brighter or longer lasting than it really was, skewing measurements of its energy and distance. That's why missions like the James Webb Space Telescope are so crucial. Their sharp infrared vision can untangle the lensed images, separating the burst's true light from the lens's warped illusions. What makes lensed gamma-ray bursts truly revolutionary is their rarity. Only a handful have ever been confirmed, each one a cosmic accident where chance alignments turn faint whispers into deafening shouts. But as telescopes grow more sensitive, these chance encounters are becoming less accidental and more like guided tours through the universe's most hidden corners. Every lensed burst isn't just a flash of light. It's a partnership between the universe's most violent explosions and its most massive structures, working together to reveal secrets neither could unveil alone. Gamma-ray bursts might be the universe's brightest explosions, but they could also hold clues to its darkest secret dark matter. Among the many wild theories attempting to explain these enigmatic flashes, one of the most intriguing suggests that some gamma-ray bursts might not come from collapsing stars or merging neutron stars at all. Instead, they could be the death throes of dark matter itself. Imagine an invisible particle, one of the building blocks of the universe's hidden mass, finally meeting its demise in a burst of high-energy radiation. That's the tantalizing possibility some physicists are exploring. though the evidence remains as elusive as dark matter itself. One leading hypothesis suggests that when two dark matter particles collide, they could annihilate each other in a violent release of energy, including gamma rays. In regions of space where dark matter is densely packed, like the centers of galaxies, these annihilations might produce signals eerily similar to short gamma ray bursts. The challenge: dark matter interacts so weakly with ordinary matter that these signatures would be incredibly faint, buried beneath the more common bursts from stellar cataclysms. Still, astronomers have sifted through gamma-ray burst catalogs searching for anomalies, events without host galaxies, bursts in unexpected locations, or energy signatures that don't quite fit known models. None have provided a smoking gun yet, but the search continues. Then there's the even more exotic idea: primordial black holes. These hypothetical objects, thought to have formed in the chaotic first moments after the Big Bang, could be another dark matter candidate. If they exist, some might be evaporating right now through Hawking radiation, ending their lives in a final, gamma-ray-filled outburst. Others could collide, sending ripples through space-time as gravitational waves while simultaneously igniting a gamma-ray burst. The Laser Interferometer Gravitational Wave Observatory has already spotted mergers of stellar mass black holes, but the hunt for smaller, primordial ones and their potential gamma-ray signatures remains open. Of course, not every unexplained burst points to dark matter. The universe is full of astrophysical oddities, from magnetars to quark novas, that could mimic some of these signals. And while no definitive link has been proven, the mere possibility keeps theorists intrigued. After all, if gamma-ray bursts could somehow reveal the nature of dark matter, they'd solve one of cosmology's greatest mysteries in the most spectacular way possible, with a flash of light from the darkest corners of the universe. Until then, every unusual burst that defies explanation adds another piece to the puzzle, reminding us that the cosmos still has surprises up its sleeve. Could gamma-ray bursts be the reason we haven't found alien civilizations? It's a haunting possibility that ties into one of astronomy's biggest mysteries, the Fermi paradox. If the universe is so vast and ancient, why does it seem so empty of intelligent life? One chilling explanation points to these catastrophic explosions as cosmic sterilizers, wiping out potential life across entire galaxies. Imagine a galaxy where advanced civilizations were just beginning to flourish until a nearby gamma-ray burst bathes every planet in lethal radiation, resetting the evolutionary clock to zero. The math is unsettling, given how common these bursts were in the early universe and how their high-energy jets can reach across tens of thousands of light-years. Entire regions of space may have been repeatedly scoured clean of complex life. We know gamma-ray bursts pack enough power to strip atmospheres and irradiate surfaces. Earth itself might have narrowly escaped this fate. Geological records show evidence of past mass extinctions that align suspiciously with the expected arrival times of nearby bursts. The Ordovician extinction 450 million years ago, which wiped out nearly 85% of marine species, coincides with a potential gamma-ray burst impact. While not proven, the scenario fits a sudden ozone layer destruction followed by intense ultraviolet radiation and global cooling. If this happened here, how many other planets endured worse? The timing adds another layer to the paradox. In the universe's first few billion years, when gamma-ray bursts were far more frequent, entire galactic neighborhoods might have been rendered sterile again and again. Emerging life would have faced a gauntlet of these cataclysms, each one potentially resetting any progress toward complexity. Even if life arose countless times, the bursts could have cooled it before intelligence had a chance to develop. This gamma-ray burst bottleneck theory suggests we might not hear from alien civilizations simply because the universe spent its early epochs violently preventing them from surviving long enough to thrive. Yet there's an ironic twist to this cosmic Grim Reaper scenario. The same heavy elements forged in gamma-ray bursts, carbon, oxygen, iron, are essential building blocks for life. So while these explosions may have sterilized vast regions, they also seeded future possibilities. It's a brutal cycle of creation and destruction, where the very forces that threaten life also provide its raw materials. Could this explain the eerie silence? Maybe. But it's also possible that resilient life finds a way hiding in protective environments, evolving radiation resistance, or even harnessing the energy of these bursts. After all, if humanity is here despite the risks, others might have beaten the odds too. The truth remains hidden in the depths of space, waiting for the next gamma-ray flash to reveal whether these explosions are cosmic killers or just one more challenge life must overcome. When it comes to raw speed, nothing in the universe rivals the jets unleashed by gamma-ray bursts, narrow beams of particles and radiation screaming through space at more than 99.99% the speed of light. To put that in perspective, if one of these jets raced past Earth, it could circle our planet 7 times in a single second. This isn't just fast, it's physics pushed to the breaking point where Einstein's theory of relativity takes center stage. The secret to these jets' blistering velocity lies in their birthplace, the chaotic environment around a newborn black hole or neutron star. As matter spirals inward at unimaginable speeds, magnetic fields twist and snap like rubber bands, funneling some of that material into tightly focused streams along the poles. These jets aren't messy explosions, they're precision-engineered particle accelerators, channeling energy so efficiently that they convert stellar collapse into focused beams with the energy of a billion suns. But here's the catch: their incredible speed makes them visible only if we're looking straight down the barrel. Gamma-ray bursts don't shine in all directions like a supernova. Instead, their energy gets concentrated into jets just a few degrees wide, meaning we only detect bursts whose beams happen to point directly at Earth. It's like trying to spot a lighthouse from across an ocean. Unless the beam sweeps over you, you'd never know it was there. This beaming effect explains why we miss countless bursts for every one we catch, and why some galaxies seem suspiciously quiet despite likely hosting these explosions. The implications of this focused power are staggering. Each jet's material moves so close to light speed that time dilation comes into play, a phenomenon where clocks aboard the jet would tick far slower than those on Earth. Particles within the jet also experience extreme relativistic effects, compressing their emitted light into shorter wavelengths and boosting their apparent brightness. That's why even a jet from the edge of the observable universe can temporarily outshine everything else in the cosmos. It's not just powerful, but its radiation gets amplified by its own mind-bending speed. Yet for all their brilliance, these jets face cosmic obstacles. As they plow through interstellar gas, they create shock waves that slow them down over time, like a speedboat hitting choppy water. The afterglow we detect, the lingering radiation across X-ray, optical, and radio wavelength, is essentially the jet's energy dissipating into its surroundings, a glowing wreckage marking where the universe's fastest particle accelerator finally met its match. Understanding these jets isn't just about studying gamma-ray bursts, it's a masterclass in high-energy physics. Laboratories on Earth can't recreate these conditions, so astronomers rely on bursts as natural experiments, testing how matter behaves under extreme speeds and energies. Every jet we detect adds another piece to the puzzle, revealing how black holes power their cosmic artillery and why the universe favors such focused, fleeting violence over chaotic, widespread explosions. So the next time a gamma-ray burst flashes across the sky, remember, you're not just seeing a distant explosion. You're witnessing a relativistic bullet fired from a cosmic gun, a fleeting beam of energy so fast and focused that spotting it at all is like winning the universe's rarest lottery. Imagine spotting the glowing embers of a cosmic explosion without ever seeing the initial flash. That's the mystery of orphan afterglows. the ghostly remnants of gamma-ray bursts that seem to appear out of nowhere, their parent explosions missing from the record books. These strange phenomena aren't just cosmic oddities, they're critical pieces of the gamma-ray burst puzzle, hinting at how many of these cataclysms we might be missing simply because we weren't looking in the right direction. The key to understanding orphan afterglows lies in the physics of GRB jets. These ultra-focused beams of energy shoot out like lighthouse beams, meaning we only detect bursts when Earth happens to lie directly in the jet's path. But what if we're just off-axis, catching the spray of radiation from the jet's edges rather than its core? In those cases, the initial gamma-ray flash might be too faint or diffuse for our satellites to spot, while the later afterglow, created as the jet slams into surrounding gas, could still be visible at longer wavelengths. It's like hearing the echo of a shout from around a corner without ever seeing the person who yelled. One of the most famous examples is GRB 160810A. When optical telescopes caught its fading afterglow in 2016, researchers scrambled to find matching gamma-ray signals and came up empty, the leading theory. Earth was slightly misaligned with the jet's central axis, placing us in the wings of the explosion rather than its bullseye. While we missed the main gamma-ray show, the jet's outer edges still interacted with interstellar material, creating an afterglow bright enough to register. The implications are staggering. If orphan afterglows are indeed off-axis GRBs, it means the universe could be producing far more of these explosions than we've ever detected, possibly 10 times as many. That hidden population would skew everything from cosmic star formation rates to estimates of how often these bursts threaten life-bearing planets. Some astronomers even speculate that orphan afterglows could explain mysterious fast radio bursts or other transient events that currently defy classification. Detecting these phantoms requires a paradigm shift in how we observe the sky. Traditional GRB hunts focus on catching the initial gamma-ray flash, but orphan afterglow searches flip the script, scanning for unexplained optical, X-ray, or radio glows that match GRB afterglow profiles. Projects like the Zwicky Transient Facility have turned this into an art form, spotting hundreds of candidate orphans by comparing nightly sky surveys for sudden, fading point sources. Yet confirming these candidates remains notoriously difficult. Without the gamma-ray trigger, astronomers must rule out other explanations: supernova, tidal disruption events, even unusual stellar flares before declaring an afterglow truly orphaned. That's where multi-wavelength follow-up becomes crucial. A genuine GRB afterglow will fade predictably across different wavelengths, its spectrum showing telltale signs of relativistic shocks. The James Webb Space Telescope has been instrumental here, using its infrared eyes to peer through dust clouds that might hide orphan afterglows in visible light. Perhaps the most tantalizing aspect of orphan afterglows isn't what they tell us about mist bursts, but what they reveal about jet structure itself. The way their light curves differ from on-axis afterglows provides a 3D map of how energy dissipates across a GRB jet's cross-section. Some show unexpected plateaus or rebrightening phases, suggesting jets aren't uniform beams but might have intricate substructures, spiral patterns, layered energy shells, or even multiple jet components firing in sequence. As telescope networks grow more sophisticated, the orphan afterglow mystery is slowly unraveling. Each new detection adds another data point to the hidden population of GRBs that flicker just beyond our direct line of sight. They remind us that for every gamma-ray burst we catch blazing head-on, there could be dozens more whispering their presence through these ghostly afterglows, cosmic fireflies we're only now learning to see. Among the universe's most extreme objects, magnetars stand out: neutron stars with magnetic fields so intense they could strip information from a credit card halfway to the moon. These cosmic powerhouses might hold the key to unlocking one of gamma-ray bursts' strangest mysteries: why some bursts, especially those from the early universe, show energy signatures that defy conventional explanations. In the metal-poor environments where the first stars formed, magnetars could have been the unseen engines behind some of the most violent explosions in cosmic history. The connection lies in how magnetars form. When a massive star collapses, it doesn't always settle quietly into a neutron star or black hole. If the star was spinning rapidly and packed with a strong magnetic field, its core might compress into a magnetar, a neutron star with a magnetic field 1,000 trillion times stronger than Earth. These fields aren't just curiosities, they're reservoirs of unimaginable energy. As a magnetar's crust shifts under magnetic stress, it can trigger starquakes, releasing violent flares of X-rays and gamma rays. In the early universe, where stars were richer in hydrogen and helium but lacked heavier elements, these magnetic monsters may have been far more common. This could explain some of the perplexing traits of high redshift gamma ray bursts. Take GRB 050904, a burst from when the universe was less than 2 billion years old. Its light curve showed erratic spikes and plateaus unlike the smooth decline of typical collapsar-driven bursts. Magnetar models fit this behavior perfectly. Instead of a single catastrophic collapse, the burst might have been powered by a magnetar's repeated energy releases, like a cosmic engine sputtering to life in fits and starts. The star's intense magnetic field could have also funneled its energy into narrower, more stable jets, producing the burst's unusual spectral lines. Metal-poor environments add another layer to the puzzle. In today's universe, heavy elements dampen magnetic field generation in collapsing stars. But in the primordial cosmos, where metals were scarce, stars could retain stronger magnetic fields as they formed, making magnetar births more frequent. This might be why some distant bursts have energies that overshoot predictions their magnetar engines had access to purer, unobstructed magnetic fuel. The smoking gun, some short GRBs typically linked to neutron star mergers, exhibit X-ray flares that linger for hours, far longer than merger models predict. Magnetar-powered explanations fill this gap. If the merger's remnant was a magnetar rather than a black hole, its magnetic field could keep pumping energy into the aftermath, stretching the burst's emission like a cosmic echo. Yet magnetars aren't a one-size-fits-all solution. Their models struggle to explain the ultra-high-energy photons seen in bursts like GRB 130427A. But as telescopes like IXP map magnetic fields around distant explosions, and simulations refine how magnetars behave in pristine cosmic conditions, these magnetic remnants are proving to be more than exotic outliers. They might be the missing link in understanding how the universe's first stars died, not with a whimper, but with a magnetically charged bang. For years, astronomers operated under a simple rule: long gamma-ray bursts meant a supernova was coming. After all, these bursts were supposed to be the death cries of massive stars collapsing into black holes, events so violent they should leave behind an unmistakable supernova signature. But then reality threw a curveball. In 2006, researchers tracking GRB 060614, a textbook-long burst lasting 102 seconds, waited for the inevitable supernova to appear. And waited and waited. Weeks passed, telescopes scanned, but the anticipated stellar explosion never materialized. This wasn't just a fluke. GRB 060505, GRB 111005A, and others followed the same baffling pattern. Brilliant gamma-ray flashes with no supernova in their wake. Suddenly, the tidy connection between long bursts and supernova had a glaring hole, and scientists were left scrambling for answers. The implications run deep. If some long gamma-ray bursts don't produce supernova, their origins might be stranger than we thought. One leading theory suggests these supernova-less bursts could come from stars that collapse directly into black holes without the dramatic stellar fireworks of a supernova. Picture a massive star so heavy and dense that when its core gives out, the entire star implodes without resistance. no rebound shockwave, no explosive ejection of outer layers. It's like a building collapsing straight into its own basement, leaving no debris on the sidewalk. For observers, this would mean gamma rays from the black hole's relativistic jets, but no luminous supernova to light up the host galaxy. Another possibility, the supernova are there, just too faint or obscured to detect. Dusty galaxies might shroud the optical afterglow, while infrared telescopes like Spitzer have occasionally spotted hidden supernova others missed. GRB 080319b, initially labeled supernova-free, later revealed a faint infrared glow consistent with an unusually dim stellar explosion. This raises a provocative question. Are we missing supernova because they're intrinsically weaker, or because cosmic dust is playing tricks on our instruments? Then there's the wild card alternative progenitors. Could some long burst stem from neutron star mergers with unusually long-lived jets, or perhaps collisions between stars and intermediate mass black holes? The rarity of these events makes them hard to confirm, but their existence would upend our classification systems. The mystery deepens when we look to the early universe. Some of the most distant gamma-ray bursts show no signs of supernova, but their host galaxies are so faint and primitive that even our best telescopes struggle to confirm or rule out accompanying explosions. This leaves open the unsettling possibility that the first stars died differently, skipping the supernova stage entirely or producing explosions unlike anything in today's cosmos. What makes the missing supernova problem so crucial is what it reveals about stellar deaths. If massive stars can bypass supernova entirely, it changes how we model chemical enrichment across cosmic history, how elements vital for life get scattered through space. It also means that gamma-ray bursts, already rare, might have an even darker subset lurking in the shadows, silent killers that vanish without a trace. Every burst without a supernova is a reminder that the universe still holds surprises, and that even the most violent deaths can sometimes leave no witnesses. Deep in the cosmic dark ages, before galaxies took shape and long before planets like Earth existed, the universe forged its very first generation of stars, celestial giants known as population 3 stars. Unlike today's stars, these primordial behemoths were made purely of hydrogen and helium, the raw elements cooked up in the Big Bang. No heavier metals tainted their cores, no stardust clouded their birth. This purity gave them extraordinary properties, masses hundreds of times greater than our Sun, surface temperatures scorching past 100,000 degrees, and lifetimes measured in mere millions of years before exploding in spectacular hypernova. If these stars still existed, we'd see them blazing across the cosmos like cosmic flares. But they vanished billions of years ago, their light long since faded into the infrared background of the universe. So how do we study these elusive stellar pioneers? The answer may lie in the gamma-ray bursts they left behind. Gamma-ray bursts from population 3 stars would be unlike anything we've detected so far. Their unique chemistry, lacking metals like carbon or oxygen, would leave distinct fingerprints in the burst's afterglow spectra. Instead of the complex absorption lines seen in modern GRBs, these ancient explosions might show only the simplest atomic transitions, the telltale signatures of pristine hydrogen and helium. Their light curves could also differ, with longer durations and higher peak energies thanks to the star's enormous masses and powerful magnetic fields. Some models even suggest these bursts would be far more common in the early universe, flickering like cosmic beacons as generation after generation of population 3 stars lived fast, died young, and seeded space with the first heavy elements. The hunt for these primordial bursts is like searching for ghostly footsteps in cosmic sands. Every high redshift GRB we detect gets scrutinized for population 3 hallmarks. Take GRB 140318A, a burst from when the universe was just 650 million years old. Its afterglow spectrum showed curiously weak metal lines, hinting at a chemically simple environment, possibly one of the last places where population 3 stars formed. Then there's GRB 200522a, whose extreme brightness and peculiar energy distribution matched simulations of metal-free stellar collapses. While neither can be definitively linked to population 3 stars, they're tantalizing glimpses of what might be hiding deeper in the infrared shadows. The challenge is separating true first-generation bursts from later metal-poor imposters. As the universe aged, some regions remained chemically pristine longer than others, meaning even comparatively young stars could mimic population 3 signatures. That's where the James Webb Space Telescope becomes essential. By peering into the infrared with unprecedented sensitivity, JWST can dissect the host galaxies of ultra-distant GRBs, looking for the absence of metal-rich stars that would confirm a population 3 origin. A burst paired with a galaxy devoid of heavy elements would be the smoking gun proof that we've finally captured the death cry of a star from the dawn of time. But why does this cosmic archaeology matter? Because population 3 stars didn't just light up the early universe, they transformed it. Their explosions forged the first heavy elements, blowing open bubbles of ionized gas that shaped future galaxies and possibly even seeded the cosmic web with magnetic fields. A gamma ray burst from one of these stars would be more than a flash in the dark. It would be a direct messenger from the era when the universe switched from simplicity to complexity. Every telescope scanning the skies for these elusive bursts is essentially looking for the matches that lit the cosmic furnace, the fiery beginnings of everything we know. For decades, the origins of gold, platinum, and other heavy elements were one of astronomy's greatest mysteries. Conventional supernova couldn't explain their abundance until August 17, 2017, when the cosmos handed scientists a smoking gun. That day, gravitational wave detectors picked up ripples in space-time from a pair of colliding neutron stars 130 million light-years away. 2 seconds later, NASA's Fermi satellite caught a short gamma-ray burst from the same patch of sky. This 1-2 punch, dubbed GW170817, wasn't just a coincidence. It was the universe showing its hand, revealing that neutron star mergers don't just produce short GRBs, they're cosmic alchemists, forging the heaviest elements in the universe. The real spectacle came in the aftermath. As telescopes swiveled to observe the collision, they witnessed something never seen before, a kilonova. Unlike a supernova's symmetrical explosion, a kilonova is a lopsided inferno, its glow powered by the radioactive decay of freshly minted heavy elements. The ejected material, a soup of neutrons and atomic nuclei combined in a frenzy called rapid neutron capture, or the R process. Within hours, this nuclear crucible produced staggering amounts of gold, platinum, and uranium, scattering them into space. Calculations suggest this single event created hundreds of Earth masses worth of gold alone, proof that the universe's most precious metals are born in the violent embrace of neutron stars. GW170817 didn't just solve the riddle of heavy elements, it rewrote the rulebook for short gamma-ray bursts. Before this detection, theorists speculated that neutron star mergers could produce GRBs, but the connection was circumstantial. The simultaneous gravitational waves and gamma rays erased all doubt, confirming that these mergers launch ultra-relativistic jets. The burst itself was unusually faint, hinting that we might have been viewing the jet slightly off-axis, a perspective that helped astronomers model jet structures with unprecedented precision. Yet the surprises kept coming. The kilonova's light curve didn't match simple predictions. Its early blue hue shifted to red over days, suggesting multiple layers of ejected material with different compositions. Some components shot out at near light speed while others meandered, creating a complex glow that telescopes are still analyzing. This messy ejection challenged assumptions about how orderly or chaotic neutron star mergers really are. The fallout extended beyond astrophysics. GW 170817 marked the dawn of multi-messenger astronomy, where gravitational waves, gamma rays, and light all tell parts of the same story. It proved that collisions we'd modeled on paper actually happen, and that they're laboratories for extreme physics. Magnetic fields in the merger's aftermath were billions of times stronger than Earth's. Particle accelerators in the debris reached energies far beyond human-made colliders, and the event's gravity provided a new way to measure cosmic expansion. But perhaps its most poetic legacy is what it revealed about us. The gold in wedding rings, the platinum in medical devices, even the uranium fueling nuclear reactors. All were likely forged in similar cataclysms billions of years ago. Every time a neutron-star merger lights up the cosmos, it's not just creating a gamma-ray burst, it's seeding future galaxies with the ingredients for planets, life, and civilizations. GW 170817 wasn't just a discovery, it was a mirror, showing us that the universe's most violent explosions are also its most creative. The hunt for gamma-ray bursts is about to take a giant leap forward, thanks to a new generation of telescopes designed to push the limits of what we can see. Leading the charge is the Vera Rubin Observatory, set to begin its decade-long legacy survey of space and time in 2025. This ground-based powerhouse will scan the entire southern sky every few nights with a 3.2 gigapixel camera, the largest ever built. Unlike current telescopes that might catch a handful of bursts by chance, Rubin's relentless surveying will spot dozens of GRB afterglows each year, many from regions of the sky other observatories miss. Its rapid alerts will give astronomers precious extra hours to study fading afterglows, especially from ultra-distant bursts whose host galaxies would otherwise be invisible. But Rubin is just part of the equation. In the coming decade, the European Space Agency's Athena X-ray Observatory will revolutionize how we study these cosmic explosions from orbit. Scheduled for launch in 2035, Athena's advanced X-ray spectrometer will dissect GRB afterglows with unprecedented precision, measuring the chemical composition of gas along their line of sight across billions of light years. Its wide-field imager can simultaneously track multiple bursts, catching subtle features in their light curves that reveal the structure of relativistic jets. Together, these instruments will transform Athena into a cosmic forensic lab, reconstructing the environments where gamma-ray bursts are born with detail we've only dreamed of. The future gets even brighter when you factor in specialized GRB hunters like ESVOM, a French-Chinese satellite launching in 2024. Designed specifically to catch the most distant bursts, ESVOM combines gamma-ray detectors with rapid-response optical and X-ray telescopes, filling a crucial niche between Swift and future missions. Its unique orbit will ensure continuous coverage of the gamma-ray sky, while ground stations in Chile and China guarantee fast alerts to telescopes worldwide. Early tests suggest ESVOM could spot bursts from the first 500 million years of the universe closer to the Big Bang than any GRB detected before. Then there's the game-changing potential of neutrino and gravitational wave detectors. Projects like IceCube Gen 2 and the Einstein telescope won't see gamma rays directly, but by catching neutrinos or ripples in spacetime from the same events, they'll provide entirely new perspectives on what powers these explosions. Imagine pinpointing a gamma ray burst not just by its light, but by the subatomic particles or gravitational waves it emits. A multi-messenger approach that could finally reveal whether some bursts come from exotic sources like dark matter annihilation or primordial black holes. This new era won't just mean more detections, it'll mean deeper science. With Rubin, Athena, and their peers working in concert, astronomers will build the first detailed maps of how GRB rates changed across cosmic history, probing whether the earliest bursts differed fundamentally from today's. They'll test if metal-poor environments really produce more energetic jets, or if the mysterious missing supernova bursts represent an entirely separate class of events. Most excitingly, these telescopes might finally catch a population 3 GRB, a burst from the universe's very first stars, settling one of astrophysics' biggest open questions. The telescopes of tomorrow are being built to answer questions we haven't even thought to ask yet. Just as Swift and Fermi revealed surprises like magnetar-powered bursts and ultra-long GRBs, Rubin and Athena will undoubtedly uncover phenomena that rewrite our understanding of these cosmic explosions. Every improvement in sensitivity, every new wavelength covered, and every second shaved off response times brings us closer to seeing the universe's most violent events not as fleeting mysteries, but as open books, written in gamma rays, X-rays, and light across the spectrum, waiting to be read. Some cosmic explosions don't just break records, they shatter them beyond recognition. On October 9, 2022, satellites orbiting Earth picked up a gamma ray burst so intense it temporarily blinded most of the instruments trying to measure it. Designated GRB 221009A, this explosion wasn't just powerful, it earned the nickname BOAT, the brightest of all time, by unleashing more energy in under 10 minutes than our Sun will emit across its entire 10 billion-year lifespan. For context, if you combined every star in the Milky Way, flashed their combined brightness for a single second, you'd still fall short of matching BOAT peak intensity. What made this burst so extraordinary wasn't just its raw energy, it was the sheer luck of its location. Unlike ultra-distant GRBs that fade into obscurity, BOAT erupted from a relatively nearby galaxy just 2.4 billion light-years away. That's practically next door in cosmic terms, meaning its light didn't stretch and dim as much as more ancient bursts, but proximity alone doesn't explain its brilliance. Analysis revealed BOAT jet was pointed almost directly at Earth, a perfect bullseye alignment that amplified its apparent brightness. Think of it like standing in front of a lighthouse's beam instead of viewing it from the side. What would normally be a narrow flash became an all-consuming glare. Yet BOAT's most puzzling feature was its aftermath. Most gamma-ray bursts fade predictably, their afterglows dimming in a smooth curve. BOAT defied expectations. Its X-ray afterglow flickered and rebrightened for weeks, as if the black hole powering it kept reactivating like a cosmic engine refusing to shut down. The Chandra X-ray Observatory caught bizarre, ring-like structures in the burst's echoes, likely caused by dust clouds in our own Milky Way reflecting X-rays like interstellar mirrors. Even more surprising, BOAT host Galaxy, normally invisible at such distances, became detectable purely because the burst briefly outshone its trillion stars combined. Theories about BOAT origins range from a hyper-rare quark nova, where a neutron star's core collapses further into exotic matter, to a supermassive star collapsing directly into a black hole with minimal supernova fireworks. Some models suggest its central engine might have been a magnetar spinning near the breakup limit, pumping energy into the jet long after the initial collapse. But perhaps the biggest lesson BOAT taught us is humility. Despite its unmatched brilliance, it wasn't the most energetic burst ever, just the one that happened to aim straight at us. For every BOAT we catch, there could be dozens of equally powerful bursts pointing elsewhere, their light lost in the cosmic dark. In the end, GRB 221009 wasn't just a scientific curiosity, it was a reminder that the universe always keeps its most spectacular fireworks in reserve, waiting for the right moment to remind us how much we still have left to discover. Most gamma-ray bursts play by predictable rules, flash brilliantly for seconds or minutes, then fade into obscurity. But scattered throughout the cosmic record are bizarre outliers that refuse to follow the script, ultra-long gamma-ray bursts, events that rage not for fleeting moments but for hours or even days. These marathon explosions don't just stretch our definitions, they hint at entirely new cosmic catastrophes unfolding in the darkness. The first clue to their strangeness came in 2011 with GRB 111209A. While typical bursts fade within minutes, this one kept shining in X-rays for nearly 7 hours, an eternity by GRB standards. At first, astronomers assumed it was a fluke. Then came GRB 130310A, glowing stubbornly for over 4 hours. Soon, it became clear these weren't anomalies. They represented a rare but distinct class of explosions with origins far removed from ordinary collapsars or neutron star mergers. One leading theory points to blue supergiants, stars dozens of times more massive than our Sun, but with outer layers so bloated they could engulf the entire solar system. When these monsters collapse, their immense size means death comes slowly. Unlike compact stars that detonate rapidly, a blue supergiant's extended envelope acts like cosmic taffy, stretching the collapse process into hours as the black hole gradually consumes its outer layers. The result, a sustained gamma-ray eruption unlike anything seen from smaller stars. Supporting this idea, several ultra-long GRB host galaxies show evidence of recent, vigorous star formation, perfect nurseries for birthing such stellar giants. But blue supergiants aren't the only suspects. Some ultra-long bursts, especially those lacking supernova signatures, might stem from tidal disruption events when a star wanders too close to a supermassive black hole and gets shredded into a glowing stream of plasma. As the debris spirals inward, it can launch jets lasting for days, mimicking a GRB's signature. GRB 110328A, with its unusual location near a galaxy's center and absence of a stellar host, fits this scenario eerily well. The challenge lies in distinguishing these two causes, since both can produce similar light curves. The rarest and most puzzling ultra-long bursts might not involve stars at all. A handful of candidates, like GRB 160509b, lasted over 10 hours with energy profiles that defy conventional models. Some theorists speculate these could be white hole eruptions, hypothetical cosmic drains where matter and energy gush outward instead of vanishing, or even signs of exotic physics like cosmic string interactions. While these ideas remain speculative, they highlight how ultra-long GRBs stretch our understanding of extreme astrophysics. What makes these marathon bursts so valuable isn't just their mystery, it's their potential as cosmic probes. Their prolonged emission allows telescopes to study jet physics in slow motion, tracking how shock waves propagate and particles accelerate over timescales impossible with fleeting bursts. Some show unexpected rebrightening phases, suggesting central engines that reactivate long after collapse, a phenomenon that could rewrite models of black hole formation. Others, like GRB 140618A, left behind unusually luminous radio remnants, tracing how the jets interacted with interstellar gas for months after the initial explosion. As observatories like the Vera Rubin Observatory come online, astronomers anticipate finding more of these cosmic anomalies, perhaps even bursts persisting for weeks. Each new discovery peels back another layer of the ultra-long GRB enigma, revealing whether they're extreme versions of known phenomena or something entirely new. For now, they stand as reminders that even the universe's most violent explosions can unfold at their own unhurried pace, challenging us to rethink what we know about stellar deaths, black hole feasts, and the limits of cosmic energy release. Measuring cosmic distances is one of astronomy's most stubborn challenges, a puzzle that's forced scientists to rely on an assortment of cosmic yardsticks: Cepheid variable stars, Type Ia supernova, even the flickering of quasars. But lurking in the background is an unexpected contender for this role: gamma-ray bursts. These cataclysmic explosions could revolutionize how we map the universe's expansion, if we can crack the code to their true brightness. The idea isn't as far-fetched as it sounds. Just as a lighthouse's apparent brightness reveals its distance if you know its intrinsic wattage, gamma-ray bursts might serve as standard candles of objects whose distance can be deduced from their observed brightness. The key lies in correlations like the Amati relation, which links a burst's total energy output to the peak frequency of its gamma rays. When this relation holds, it suggests GRBs might follow predictable brightness patterns, making them cosmic beacons visible across the observable universe. Unlike supernova, which fade after weeks, GRBs can be spotted from much farther away, some from regions so distant their light has traveled for over 13 billion years. Yet turning GRBs into reliable distance markers is no simple task. Supernova earned their role as standard candles through decades of calibration. Type Ia supernova explode with near-identical brightness because they originate from white dwarfs crossing a strict mass threshold. Gamma-ray bursts, by contrast, are messy. Their brightness varies wildly depending on jet structure, viewing angle, and the properties of their progenitor stars. A burst viewed head-on might appear 1,000,000 times brighter than the same event seen from the side, and without knowing the jet's orientation, extracting its true energy becomes guesswork. Efforts to refine GRB distance measurements have yielded mixed results. Some studies, like those analyzing bursts with both redshift and afterglow data, show promising consistency with the Amati relation. GRB 050824, for instance, matched predicted brightness within 10%, close enough to hint at underlying order, but outliers abound. GRB 980425, a nearby burst, was so faint it nearly broke the correlation entirely, suggesting some bursts either operate by different rules or suffer from unseen factors like extreme dust absorption. The stakes go beyond academic curiosity. If calibrated properly, GRB distances could probe cosmic expansion in epochs where supernovae are too faint to see, especially during the universe's dark ages, before galaxies fully formed. They might also resolve discrepancies in Hubble constant measurements, where supernova and cosmic microwave background data stubbornly disagree. A third, independent method could break the deadlock. New telescopes offer hope. The James Webb Space Telescope's infrared capabilities could dissect ultra-distant bursts with unprecedented precision, while next-generation gravitational wave detectors might independently confirm merger distances for short GRBs. Until then, gamma-ray bursts remain tantalizing but temperamental yardsticks, cosmic lighthouses flickering through the fog, waiting for us to decipher their true brilliance. Some gamma-ray bursts defy explanation not by how they shine, but by where they seemingly don't come from. Flashes of energy so isolated that they appear to erupt from the void itself. These ghost GRB events with no detectable host galaxy in their aftermath present one of modern astronomy's most haunting puzzles. Imagine tracing a firework back to its launch site, only to find empty sky where the launch pad should be. That's the enigma astronomers face when studying bursts like GRB 070125, whose brilliant afterglow faded to reveal nothing. No spiral arms of a massive galaxy, no faint smudge of a dwarf system, just the cosmic equivalent of a blank canvas. Theories about these phantom explosions split into two camps. One suggests ghost GRBs originate in galaxies so distant their light has been stretched beyond detection by cosmic expansion. At redshifts beyond 7, even the brightest galaxies vanish into infrared darkness, their starlight diluted by 13 billion years of interstellar dust and gas. In these cases, the burst itself acts like a flare shot into a fog bank, visible briefly, but leaving no trace of its source. Supporting this idea, some ghost bursts exhibit absorption lines from primordial gas clouds along their line of sight, hinting they traversed unthinkable distances before reaching us. The second possibility is even more intriguing. These bursts might come from ultra-faint dwarf galaxies, stellar backwaters so sparse they're virtually transparent to our telescopes. These galactic minnows, sometimes containing just a few million stars, lack the heavy elements and dust that make larger galaxies visible across cosmic distances. Yet their metal-poor environments could be ideal breeding grounds for the massive, unstable stars that produce long GRBs. When the Hubble Space Telescope scrutinized the location of GRB 060505, another ghost burst, it found a dim patch of light 1 billion times fainter than the Milky Way. This barely their galaxy, likely filled with first-generation stars, would have been invisible without the burst's backlighting. But the plot thickens with bursts like GRB 110112A, which showed no host galaxy even when observed by the James Webb Space Telescope's ultra-sensitive infrared eyes. This raises a third, more radical idea. Some ghost GRBs could be intergalactic strays, born from stars flung out of their home galaxies during violent mergers or close encounters with supermassive black holes. These rogue stars, adrift in the darkness between galaxies, would explode in total isolation, leaving no galactic address for astronomers to trace. The implications ripple outward. If ghost GRBs confirm the existence of a hidden population of dwarf galaxies or intergalactic stars, they could reshape our understanding of cosmic structure. Current models suggest these faint galaxies outnumber bright ones by 100 to 1, meaning ghost bursts might be pointing us toward the universe's most common, yet most elusive stellar habitats. Every time a GRB flashes from the apparent void, it's not just a mystery, it's a potential roadmap to the cosmos's darkest, most overlooked corners. In the hunt for gamma-ray bursts, astronomers are turning to an unlikely ally, artificial intelligence, capable of spotting these cosmic explosions in data streams faster and more accurately than any human. With observatories like the Vera Rubin Observatory set to flood scientists with petabytes of nightly sky surveys, traditional analysis methods are buckling under the sheer volume. Machine learning algorithms trained on decades of GRB light curves and spectra now sift through this deluge in real time, flagging potential bursts that might otherwise slip through the cracks. Take the case of GRB 220729A, a faint high redshift burst discovered not by a scientist scrutinizing graphs, but by an AI model scanning Fermi satellite data. The algorithm noticed subtle gamma-ray fluctuations buried in noise patterns too nuanced for human eyes to discern, leading telescopes to confirm a burst from 12.8 billion light-years away, one of the most distant ever recorded. What makes AI indispensable isn't just its speed, but its ability to classify bursts by type and origin before follow-up observations even begin. Deep learning models, fed on simulated and historical GRB data, can predict within seconds whether a new detection likely stems from a collapsar, neutron-star merger, or something more exotic. This rapid triage is crucial for prioritizing telescope time, especially when chasing the rarest high-Z events. In 2023, an AI system at the Zwicky Transient Facility autonomously identified GRB 230315b as a potential ultra-long burst candidate, a prediction later verified by Swift's X-ray telescope, which caught its unusual 4-hour afterglow. Without AI's instant analysis, this oddity might have been dismissed as noise. The real frontier, though, lies in unsupervised learning algorithms that uncover entirely new GRB subtypes by detecting anomalies in datasets. In 2021, a neural network analyzing Compton Gamma-ray Observatory archives flagged a cluster of bursts with peculiar energy distributions, now theorized to be magnetar-powered events previously lumped in with ordinary long GRBs. Another model scanning radio afterglows found a subset with bizarre rebrightening patterns, hinting at dense interstellar environments that may trace hidden galaxy formation zones. These discoveries aren't just expanding GRB taxonomy, they're rewriting how we think about stellar deaths across cosmic time. Yet AI's greatest contribution may be solving the needle in 100 haystacks problem of population 3 bursts. By training on simulations of metal-free star collapses, machine learning can target chemical signatures in afterglow spectra, like the absence of carbon absorption lines that human analysts might overlook. Projects like the James Webb Space Telescope's AI-assisted spectral pipeline aim to automate this search, scanning each new burst for primordial fingerprints as telescopes push deeper into the universe's first billion years. Of course, these tools aren't flawless. AI models can inherit biases from their training data, and false positives like flaring stars or instrument glitches mimicking GRBs still require human vetting. But as algorithms grow more sophisticated, they're becoming less like tools and more like collaborators, uncovering connections no researcher would think to test. The next chapter of gamma-ray burst science won't just be written by astronomers peering through telescopes, but by neural networks parsing the cosmos in ways we're only beginning to imagine. For all we've uncovered about gamma-ray bursts, the most thrilling discoveries may still lie ahead, pushing beyond what our current telescopes can see, toward the very edges of time itself. One of the biggest unanswered questions is whether we'll ever detect a burst from the universe's first few minutes, a relic of the Big Bang's unimaginable violence. While traditional GRBs stem from dying stars or colliding neutron stars, physicists speculate that the infant cosmos might have birthed its own breed of primordial bursts. Picture space itself seething with energy in those first chaotic moments, as quantum fluctuations ignited fleeting fires that could have left gamma-ray imprints across the cosmos. These hypothetical cosmological GRBs would be fossils of creation, carrying clues about inflation, dark matter formation, or even the birth of spacetime's fabric. Yet the challenges are immense. Any burst from the universe's first seconds would have its light stretched beyond recognition by cosmic expansion, its gamma rays redshifted into undetectable radio whispers. Even more confounding, the plasma-filled early universe was opaque to radiation, meaning light from these events might have scattered endlessly before space became transparent. That hasn't stopped theorists from proposing wild ideas, like bursts triggered by evaporating primordial black holes or phase transitions in the fundamental forces. Some models suggest these explosions could have left subtle ripples in the cosmic microwave background, patterns we might one day decode with next-generation telescopes. Closer to the realm of observation are the puzzles surrounding population 3 GRBs, those elusive explosions from the universe's first stars. No confirmed examples exist yet, but their discovery would rewrite our understanding of cosmic dawn. Were these bursts more energetic than modern counterparts, fueled by stars hundreds of times the Sun's mass? Did they lack heavy element signatures entirely, their afterglow's pristine fingerprints of hydrogen and helium, and crucially, could they help pinpoint the moment when the first black holes began shaping the cosmos? Current instruments like JWST are tantalizingly close to answering these questions, with every high redshift burst candidate scrutinized for traces of metal-free environments. Then there's the enigma of dark matter's potential role. While most bursts fit neatly into stellar collapse or merger models, a handful exhibit anomalous energy distributions or environments devoid of host galaxies. Could some be flares from dark matter particles annihilating in dense halos, or signatures of primordial black holes colliding in the void? The answer might lie in multi-messenger astronomy, correlating GRBs with neutrino detectors or gravitational wave observatories to spot exotic origins. Projects like IceCube Gen 2 and the Einstein telescope could turn this speculation into science, searching for coincident signals that no stellar process could explain. Perhaps the most profound frontier is using GRBs to test the universe's fundamental constants. Some theories suggest physical laws might vary across cosmic time or space. Gamma-ray bursts, especially those at extreme redshifts, act as natural laboratories for this. Their afterglow spectra contain absorption lines from atoms whose properties depend on constants like the fine structure constant. By comparing these lines to lab measurements, astronomers can check if physics itself has evolved. Early results are inconclusive, but future missions like Athena aim to analyze bursts with precision that could settle the debate. What unites these questions is their sheer scale. They're not just about understanding explosions, but about reconstructing the universe's deepest history. Each gamma-ray burst, from the faintest orphan afterglow to the boat-blinding flash, is a piece of a puzzle spanning 13 billion years, with upcoming observatories like the Vera-Rubin telescope and ESVOM set to discover thousands more bursts. We're not just mapping stellar deaths. We're assembling a timeline of cosmic evolution itself, one cataclysmic flash at a time. The ultimate fate of GRB research might be to reveal not just how stars die, but how everything began. From colossal hypernova to ghostly orphan afterglows, these 30 facts reveal why gamma-ray bursts aren't just cosmic explosions, they're time machines. Each distant flash carries whispers from an era when galaxies were raw and unformed, when the first stars lived fast and died violently, seeding the void with the elements that would one day build planets and life. Think about GRB 090423. It's light traveling 13 billion years just to tell us how quickly the universe woke from darkness. Or the boat record-shattering brilliance, proving that even now the cosmos can unleash energies beyond comprehension. These bursts have rewritten astronomy's playbook, exposing primordial chemistry in their spectra, revealing hidden galaxies through gravitational lensing, and even challenging whether dark matter might lurk in their shadows. What makes them truly extraordinary isn't just their power, it's their duality. They destroy and create, sterilizing entire galactic neighborhoods with radiation while forging gold in neutron star collisions. They hide and reveal, their jets pointing our way by chance while their orphaned afterglows hint at legions we never see. And they connect us across time, with population 3 bursts promising a glimpse of the universe's first starlight, and ultra-long GRBs stretching stellar deaths into days-long cosmic operas. Every detection peels back another layer, showing us that the early universe wasn't some tranquil nursery. It was a riotous construction site, where stars the size of solar systems collapsed in seconds, where magnetic monsters spat jets across the dark, and where the seeds of everything we know were forged in these fleeting explosions. So the next time you look up at the night sky, remember, you're not just seeing stars, you're seeing the aftermath of gamma-ray bursts that shaped cosmic history, flashes so powerful they outshone the universe's youth. And with new telescopes hunting these explosions deeper into space and farther back in time than ever before, who knows what revelations the next burst might bring. If you're as captivated by these cosmic mysteries as we are, hit subscribe, because the universe is far from done surprising us. After all, the greatest lesson gamma-ray bursts teach us is simple. The cosmos isn't just stranger than we imagine. It's stranger than we can imagine.